Hello, E&M students. This is a very brief summary of some key ideas from Chapter 6, Magnetic Fields in Matter, which is the magnetic version of Chapter 4 that we spent some time studying, Electric Fields in Matter. Because of time constraints, though, in class, I'm going to just do a quick overview of the key ideas in Chapter 6. Much of the ideas are analogous to what we did in Chapter 4. So now we're going to take a chunk of matter and we're going to immerse it in an external magnetic field, as my first picture here shows. What will be the effect on the atoms and molecules inside? And the bottom line is that in many cases, you will get an induced magnetic dipole moment, which we will think of as being little loops of current inside on the atomic scale. And my sketch here shows the chunk of matter with a whole bunch of little current loops, each with a magnetic dipole moment, little m arrow. And I have shown the picture as if the chunk of matter is what's described as paramagnetic. And in a paramagnetic material, these induced little magnetic dipole moments, little m arrow, are roughly, basically, in the same direction as the external magnetic field that is causing them. That's a paramagnetic material. You can have situations where you have diamagnetic behavior, and then the alignment of the little magnetic dipole moments, little m arrow, is opposite to the external field. But my picture is drawn for paramagnets, and paramagnets are a bit more common than diamagnets. And the way this happens in a paramagnet is the magnetic dipole moment, little m, experiences a torque from the external magnetic field. And that formula for that torque is right there. N arrow equals m arrow cross b arrow. Note the electrical version of that, which we studied in Chapter 4. If you have an electric dipole moment, p arrow, in an external electric field, E, you get a torque on that, P cross E. Well, here we have the magnetic version. The magnetic torque is M cross B. Okay, so however you get it, let's imagine that we've got a chunk of matter that has a bunch of magnetic dipole moments, little m arrow, throughout it. We are going to define a new quantity now called magnetization, capital M arrow. And its definition is magnetic dipole moment per unit volume. Remember in Chapter 4, if we had a chunk of matter in an electric field, we talked about polarization, capital P. And that was electric dipole moment per unit volume. Well, this is the magnetic version. What's the SI unit of magnetization? You take the SI unit of magnetic dipole moment, which, as we discussed in the very end of Chapter 5, magnetic dipole moment has unit of current times area, ampere times meter squared, and magnetization is magnetic dipole moment per unit area, so that's ampere times meter squared over meter cubed, so that's ampere over meter. Just by way of checking, for polarization in Chapter 4, the SI unit was Coulomb per meter squared. Okay, so now, having magnetization, let's just worry about the fact that we've got a chunk of matter and it has magnetization. Just like in Chapter 4, when we had a chunk of matter with polarization, we could think of that as producing bound charge, volume bound charge density, and surface bound charge density. And now we want the magnetic version of that because we have a magnetization. And that's going to create what we're going to call bound current densities. So here's a chunk of matter that's got some magnetization throughout it. It may or may not be uniform within there. And it's got some surface, of course, this chunk of matter. And at each little point on that surface, you can draw a normal unit vector, like right there, n hat, perpendicular to the surface and outward. I will just tell you that the expression for the volume bound current density due to the magnetization, capital J sub B is curl of M. I will remind you in the electrical case, chapter 4, bound volume charge density, rho sub B, is negative divergence of polarization. So here's the magnetic version. Volume bound current density, J sub B, is curl of M. And the corresponding surface bound current density, K sub B, is M cross N hat. In the electrical case, the bound surface charge density was P dot N hat. So instead of dots, now you've got crosses, basically. And instead of big P, you've got big M. And then, knowing what the volume-bound current density and the surface-bound current densities are for the given magnetization, you can calculate the magnetic vector potential at any point somewhere. You've got some origin somewhere out here. You want to calculate the magnetic vector potential, A of R. You do that as if you would for any volume-bound current density and surface-bound current density. Mu 0 over 4 pi integral over the volume of J sub B over script R, and then another term, mu 0 over 4 pi integral over the closed surface, K sub B over script R. I will remind you that the electrical analog, chapter 4, if you had a chunk of polarized material, polarization big P, you would calculate the electric potential out at your point R. It had a term from the volume bound charge density, and it had a term from the surface bound charge density. And now we're just doing the magnetic version of that. Okay, so very similar to what we did in chapter 4. Here's another thing we're going to do because it's convenient. Introduce one more kind of vector field. And it's in fact basically the last vector field in electricity and magnetism that we have to deal with. I call it here the auxiliary field. There is no great name for it. Its symbol is a capital H arrow. It's a vector field. And Griffiths just recommends calling it the H field. Warning, some books will call this the magnetic field. Griffiths does not recommend doing that, and I agree with him. We will just call it the H field. Here's how we'll define it. We'll start from a basic principle, Ampere's law, which says that the curl of the magnetic field, B arrow, is given by mu 0 times the volume current density, J. All the volume current density, all of it. We will now break that J up into two parts. A volume current density coming from bound charge, B, and a volume current density coming from any other kind of moving charge. If it's anything that's not from bound charge, and that's going to be called free current density, J sub F. We just break up the J into those two contributions. But we already know that J bound is equal to the curl of the magnetization. So let's make that replacement. And then let's take the curl of M over to the other side and group it with the curl of B. And now we're taking the curl of this combination. And I divided both sides, by the way, by mu 0. B over mu 0 minus M. And then on the right-hand side, I have only J free. And then that motivates us to define this new vector field, H arrow, as B arrow over mu 0 minus M. So H arrow, this new vector field H, has the same units as magnetization. But if we make that definition, then Ampere's law for this new vector field H takes on a pretty simple form. The curl of H is J free. The curl of this new vector field H is determined by free volume-bound currents. In chapter 4, we introduced a new field called D, called the electric displacement, and the divergence of D, divergence, was determined by free bound charge. This is the magnetic version of that with the new vector field called H. You can think of that as Ampere's law for magnetic materials, differential form. If you integrate both sides of that over a surface bounded by a closed loop and apply Stokes' theorem, you can get the integral version of Ampere's law for magnetic materials. the line integral around a closed path of H dot dl equals the total free current that is enclosed by the path. The magnetic version, the integral of d dot dA over a closed surface, is equal to the total free charge inside. And then the last idea is if we have a special kind of material called a linear magnetic material. And for such a material, the magnetization at any point inside is directly proportional to this new field H. And the proportionality constant, which is dimensionless, is called the magnetic susceptibility, chi sub m. And chi sub m is positive if the material is paramagnetic, so that m and h are in the same direction. And chi sub m is negative if the material is diamagnetic, so that m and h are in opposite directions. And so if you have a linear material, you can take the defining formula for H and just rearrange it for B. That gives you this. And then where you have the M, you can replace it with the magnetic susceptibility times H, and you get this. And then you can do a little factoring, and you get this, mu 0 times 1 plus chi sub m times H. And then we define mu to be the magnetic permeability of the material. Note the electrical case. The electric permittivity of the material was given by that expression. And with that simple form, there's a simple relationship between B and H in a magnetic material. B equals mu H. Here's the electrical version. So it's very similar with Chapter 4 in a lot of ways. Okay? And if you're more than welcome to read more in Chapter 6 if you're interested in magnetism. But that's all I'm going to say so that you have some little bit of introduction to H, this H field. And I'll just give you an extra final warning that a lot of physicists will call H the magnetic field. And they'll just say the words magnetic field, and you might be thinking B, but they might be thinking H. That's actually sloppy on their part if they do. They ought to reserve magnetic field for B, and then use some other name for H. If nothing else, just H itself. That's my quick overview of Chapter 6, and I hope that's a little bit helpful to you, and that's all for this video.